Hello, everyone. It is my great pleasure to present our recent research on detecting memory leaks in operating system kernels. My name is Wenwen Wang, and I'm from the University of Georgia. Now, let's start. As we know, memory leaks are a common class of memory management bugs. A memory leak is triggered when a dynamically allocated memory object is not freed after its usage. Since the leaked memory objects still occupy the valuable memory resource in the system, memory leaks can cause serious system problems, especially in critical software systems. For example, the leaked memory objects can reduce the memory resource available for usable application. This can lead to significant influence on system response time and throughput. Once the memory resource exhausted, the system has to be rebooted for better efficiency and reliability. Also, memory leaks can be leveraged to launch security attacks. This has been demonstrated by vulnerabilities listed in CVE. Therefore, it is important to detect and fix memory leak bugs in software systems. To this end, many memory leak detectors have been developed. For example, address sanitizer can detect a broad range of memory safety errors, including memory leaks, by instrumenting program source code at the compilation time. Another example is memcheck, which is based on the binary instrumentation framework Wang without the requirement of program source code. Besides, the Linux kernel has a memory leak detector, which uses a garbage collection-based algorithm to detect memory leaks. In addition to this detector, there are many other memory leak detection techniques and tools. However, even with these detectors, it is still quite challenging to detect memory leaks in operating system kernels, which are a fundamental class of system software. For example, the Linux kernel memory leak detector is a dynamic detection tool and inevitably has the well-known coverage issue. That is, it cannot detect memory leaks in the kernel code that is not executed or tested at runtime. On the other side, existing static memory leak detection techniques are mainly developed for user-level applications. It is not easy to apply them directly to operating system kernels due to the inherent complexity of operating system kernels. For example, the Linux kernel has more than 25 million source code lines, with several hundred source lines added or updated every hour. This makes it difficult for static detection techniques to complete the detection of memory leaks for the entire kernel within an acceptable time. Therefore, it would be desirable to develop an effective and scalable static memory leak detector for operating system kernels. In this work, we focus on memory leaks on an early exit path. This is inspired by the observation that software bugs often lurk in rarely tested program paths. Now, let's see what is an early exit path. In general, an operating system kernel needs to handle various expected and unexpected system states. During the execution of a kernel routine, it is often necessary to exit from the routine without executing the following code because, for example, a specific system state is encountered. This is usually achieved by composing early exit paths. That is to say, early exit paths are designed to exit from kernel routine as soon as possible. As shown in the example on this slide, the source code line from 5 to 9 form an early exit path. In fact, exception or error handlers are common examples of early exit paths. But our study finds that early exit paths are also used for many other purposes in operating system kernels. For example, bypassing irrelevant kernel states and extending kernel functionalities. Moreover, some actual code often need to be executed before a kernel routine is exited from an early exit path. Like in this example, a lock is released and a memory object is deallocated on the early exit path. Therefore, if an early exit path is created without the required work, software bugs will be introduced. In particular, if a memory deallocation is required but missed on an early exit path, a memory leak will be constituted. Based on this observation, we develop MLEE, a static memory leak detector, to find memory leaks on early exit paths. The idea of MLEE is inspired by our study of early exit paths in operating system kernels. Specifically, we found that the inconsistencies of memory deallocations showing up on different early exit paths and normal paths usually indicate potential memory leaks. Therefore, it is possible to detect memory leaks on early exit paths by cross-checking the presence of memory deallocation on different early exit paths and normal paths. This is the high-level idea and approach of MLEE. Now let's see how MLEE works. MLEE takes as input the RVMIR of the target kernel and reports the memory leaks detected on early exit paths. The first step of MLEE is to identify early exit paths in the target kernel. This is done by analyzing conditional branches in each kernel routine. Next, MLEE collects memory deallocation in the same kernel routine as the identified early exit path, and checks whether there is any memory deallocation that is missed on early exit path. That is, the memory object freed by the memory deallocation is not freed on the early exit path. If such a missed deallocation is found, MLEE further analyzes the missed deallocation and the corresponding early exit path to determine whether the missed deallocation should show up on the early exit path. If yes, a potential memory leak will be reported. After manual investigation, we can confirm the bug. To put MLEE into practice, we need to address two technical challenges. The first challenge is how to identify early exit paths. Given the diverse semantics and usage scenarios of early exit paths, it is quite difficult to precisely identify early exit paths in operating system kernels. To address this challenge, we manually studied the structures and semantics of many different early exit paths in real operating system kernels, such as Linux. Through this study, we find out that the key to identify an early exit path is to identify the unique program statements that can distinguish this early exit path from other program paths in the same kernel routine. Moreover, these statements usually start from a particular conditional branch. We call such a branch an early exit branch. Therefore, by identifying early exit branch in a kernel routine, MLEE can identify early exit paths. More details about how to identify early exit branch can be found in our paper. The second challenge is how to analyze memory deallocation. Specifically, a missed memory deallocation may be not needed on an early exit path. There are many potential reasons for this. For example, the memory object freed by the missed memory deallocation may be invalid on the early exit path. Therefore, it is not appropriate to free it. To address this challenge, MLEE creates several static analyses to ensure that the memory object to be freed is live, valid, and not used on the early exit path. Besides, MLEE also heuristically infers whether the missed deallocation is necessary on the early exit path. This way, MLEE can detect memory leaks by analyzing missed memory deallocations. We have implemented MLEE as an RVM tool with multiple analysis passes. The version of the RVM is 8.0. To evaluate the effectiveness of MLEE, we applied to the Linux kernel, version 5.0. We compare the Linux kernel to RVM IR with the all yes option and feed MLE with the compiled IR. Eventually, MLE finishes the detection process for the entire Linux kernel in around half an hour. This shows the efficiency and scalability of the analysis in MLE. Next, let's see some analysis results. This table shows some statistics of the analysis results. As shown in this table, there are more than 7,000 kernel routines that have both early exit pass and memory deallocation. This demonstrates that it is very likely to have memory management operation on early exit pass. After the analysis, MLE reports 126 suspicious early exit branches with missed memory deallocation. These early exit branches are located in different kernel modules. With further manual analysis and investigation, we can finally confirm memory leak bugs. On average, it took around 3 to 5 minutes to manually analyze one suspicious early exit branch. Finally, we confirmed 120 new memory leaks related to 103 reported early exit branches. The reason we have more memory leaks than early exit branch is because one early exit branch may have multiple missed deallocations. Among the confirmed bugs, 103 bugs have been fixed using either our patch or other patches. This shows the capability of MLE to find memory leaks in real-world operating system kernels. We also studied the kernel module from which the memory leaks are discovered. As shown in the table on the right side, around 60% of memory leaks are found in drivers. This implies that drivers are one of the most buggy modules in the kernel. At the same time, this also shows that non-driver kernel modules also suffer from memory leaks. This slide shows a real memory leak bug found by MLE in the Linux kernel. In this bug, there is an early exit pass formed by the if statement from line 6 to line 9. On this early exit pass, the memory object RSS map pointed to indir QP is not freed and thus lead to a memory leak. MLE successfully detects this leak by reporting the memory deallocation at line 11 is missed on the early exit pass. This bug has been fixed in the latest Linux kernel. As a static memory leak detector, MLE also has some limitations. First, MLE may have false negatives, as it mainly focuses on memory leaks related to early exit pass. Second, MLE may also report false positives. For example, a memory deallocation missed on an early exit pass may be invoked in a callback routine or by another kernel thread. More accurate and semantic-based static analysis are required to eliminate these false positives. We leave this as part of our future work. To summarize, memory leaks in critical system software can cause serious performance, reliability, and security issues. In this work, we present a static memory leak detector called MLE to detect memory leaks in operating system kernels. MLE focuses on memory leaks on early exit paths, as they are often rarely tested in practice. After applying MLE to the Linux kernel, we found 120 memory leak bugs, and most of these bugs have been fixed in the latest Linux kernel. We believe with more tools like MLE, more memory leaks can be found and fixed in critical system software. This is my talk. Thanks for your attention, and I would be happy to take questions.